Okay, so hopefully you have come to this video from either being in class or from watching the video about page 2 of the notes, because we're going to continue what we were doing there. So on page 2, what we did was I just gave you a table of a function's derivatives at a certain value, and we constructed a polynomial that had the same properties as whatever the function was. In this case, we're going to make it make a little more sense. So this is something that you actually would do. I mean, the previous problems were just kind of like weird to get you used to it. But we did discover a sort of pattern to these polynomials that we're writing. And the pattern seemed to be we have the nth derivative, x minus a to the n over n factorial. Like that term shows up. So when we knew the fourth derivative, we would know that it'd be the fourth derivative at that point, x minus a to the fourth over 4 factorial. We're going to use that here because we could go through and integrate, but we're just going to get the same exact pattern again. So let's take a look at a problem. So what we want to do is we have f of x is sine of x, and what we're going to do is we're going to try to write a fifth degree polynomial that matches the derivatives of sine up to the fifth degree. So I need the first five derivatives of sine. So the 0th derivative is actually sine of x. So that's kind of a convention that you need to understand so that we can kind of do the problems. And then I'm just going to write down the derivatives of sine. So I get cosine, I get negative sine, negative cosine, back to positive sine, back to cosine. And now what I need to do is I need to evaluate all of those derivatives at 0, but fortunately I memorized the unit circle, so I can just kind of fly through that. So these are quadrantals, which is even easier. So it's 0, 1, 0, negative 1, 0, and 1. Okay, so now what I'm going to do is I'm going to write my polynomial, and I'm going to follow the pattern exactly, including writing a lot of things that are kind of useless. So first term, it's the 0th derivative is 0, so it's 0 over 0 factorial x minus 0, but I'm not going to write the minus 0 because that's like a lot of wasted writing. So it's x minus 0 to the 0. The next thing is 1, so the first derivative is 1, so it's going to be plus 1 over 1 factorial, x minus 0 to the first, then it's 0. So I'm going to write this even though it drops out. So it's plus 0 over 2 factorial, x squared, then it's going to be minus 1 over 3 factorial, x cubed, plus 0 over 4 factorial, x to the 4th, and then plus 1 over 5 factorial, x to the 5th. So that's just following the pattern. If I had started at the 5th derivative and integrated up and up and up, this is exactly what I would have gotten. So I'm going to clean this up because I don't really want all that extra garbage. So I have that. Notice that sine is an odd function. I'm just getting odd powers here. It's alternating, meaning that the first term is positive, the next one's negative, next one's positive. If I kept going, the next term would be negative, and so on. The pattern holds forever for this particular function. So this is approximately equal to sine of x. What do I mean by that? It's kind of a bigger idea than a tangent line. It's like taking a tangent line up a notch. So if I look at a graph, so this is a graph of sine of x and this polynomial. And so sine of x is obviously sine of x, and the polynomial is the other one. But if you look at that graph, in this interval right here, that polynomial is doing a great job. It's a really good fit. And that's the idea, is that these polynomials that we're constructing do an amazing job of approximating the function. And the more terms we add to our polynomial, the better job they'll do. We'll get into eventually like over what interval and all that, but that's the idea. So let's do another one. So say I have cosine of 2x. So the process is exactly the same. So I'm going to do a 6th degree polynomial in this case. So I need the derivatives. So I'm going to use exponents instead of actually writing out those powers. So I'm not going to write 4, 8, 16. I'm going to write to the 2nd, the 3rd, the 4th, the 5th. So chain rule all the way through. Plugging in 0 to this is still easy, which is nice. Generally speaking, you only want to try to write these polynomials at values where the derivatives are easy to evaluate. But that's not universally true. That's just kind of the lazy man's approach. So now let's write our polynomial. So p of x is equal to, so it's going to be 1 over 0 factorial x minus 0 to the 0 plus 0 over 1 factorial x minus 0 to the 1. minus 2 squared over 2 factorial x squared. So I'm always just taking the nth derivative over n factorial and then x minus 0 to the n, but I'm not writing x minus 0. So the pattern continues. So on each of these, I mean, you want to take a look at the table, take a look at the term, make sure you're kind of connecting them in your head. The sooner the better, really. So 6th derivative over 6 factorial, x to the 6th. So we get that. And then obviously I want to clean this up a little bit, but not so much. You'll get used to the fact when you're writing these kinds of polynomials, you tend to leave factorials rather than simplify them. You tend to leave exponents rather than simplify them, just because the pattern is more obvious if you do that. So this is approximately cosine of 2x. It's not actually cosine of 2x, but on a certain interval it does a really good job. And if I could keep going forever, there are ways of showing that it actually is equal. So if it's an infinitely long polynomial, it's very strange. So let's look at the graph. So this graph of cosine and the polynomial, you can see that it's doing an amazing job. Kind of, well, between -1 and 1 for sure, but kind of in that little window there. It's a really, really good fit. You go beyond that and it's a very bad fit. So the number of terms you use in the interval is very important for this. Let's do another one. So this one will be a little different. So I'm on page 3 of the notes now, if you're following along. So f of x is the natural log of x. I assume that I'll link to the notes in the description of the videos. It seems like a good thing to do. So f of x is the natural log of x, and I want to write this polynomial at x equals 1. So this one is going to require more writing. So here's the table. Let's fill it in. So I'm going to do something a little weird here. The 0th derivative is the function, so that's natural log of x. The derivative of that is 1 over x, but I'm going to write it as x to the -1. The derivative of that, because now I can just use the power rule a lot, which is what I was kind of going for. So it's -x to the -2, 2x to the -3, -6x to the -4, 24x to the -5th, and then -120x to the -6. If you're really familiar with factorials, you might notice that those coefficients are factorials. So that's going to kind of come into play because of some simplifications that I can do. Now I'm going to evaluate at 1. So one reason that I didn't choose 0 for this particular polynomial is that natural log is not defined at 0, nor any of its derivatives, obviously, because if it's not defined, how could the derivatives be? And also 1 is super easy to plug in. So I get this. Okay. So a lot of the choices that we make are really for convenience, but they just make everything work out nicely. So let's write our polynomial. So p of x is going to equal 0 over 0 factorial x minus 1 to the 0. Okay, so that's not bad. That's just 0. That's gone. So now it's going to be plus 1 over 1 factorial x minus 1 to the first. Biggest mistake that people make, or I should say the most common, I guess, is they forget to center the polynomial, so they forget to include the value at which they, or the x-coordinate at which they evaluate all the derivatives. It's got to be x minus a, so we're calling that a. So it's x minus a to the n. The nth derivative at a, x minus a to the n over n factorial, is kind of the general term here. So now I'm going to go with minus 1 over 2 factorial, x minus 1 to the 2, plus 2 over 3 factorial, x minus 1 cubed, minus 6 over 4 factorial, x minus 1 to the 4th, plus 24 over 5 factorial, x minus 1 to the 5th. So it should be comforting, I guess, to know that this pattern works, because it means that you don't have to remember an infinite number of things. There's only really one thing, and then you have to calculate a lot of derivatives and evaluate them and all, but it's much easier than it would seem kind of from the outset. So this actually simplifies quite a bit because of the way that factorials work. So the very first term is gone, and then 1 over 1 factorial is just 1, x minus 1 to the first, so I'm going to leave that in parentheses, but it's x minus 1. Now looking at the second thing, 2 factorial is just 2, so it's really just minus x minus 1 squared over 2. 2 over 3 factorial is actually just 3, so I get plus x minus 1 cubed over 3. Then I get, it just keeps going like that. So it turns out, like, if you wanted to, you could actually write the nth term of this. It's, what do we have, like, -1 to the n plus 1, x minus 1 to the n over n, I guess, would work out. I didn't write that down because it's not super important for this, but it would work out, which is kind of interesting. So that's approximately the natural log of x, which is interesting, right? Because like, how do you approximate values of natural log, or how do you just get values of natural log? Well, one way to do it is write this polynomial and plug into the polynomial instead. Polynomials are just a matter of time before you get an answer. You might not want to, but you can plug into a polynomial. Whereas if I tell you to approximate the natural log of 1.1, what are you going to do? I don't know what you would do. Other than maybe a tangent line, go from there. Let's take a look at the graph. So natural log of x is kind of the always increasing one. The polynomial is the one that increases for a while and then dips down. But you can see that on a certain interval, this interval right here, it's doing an amazing job. So it's a really nice fit. And that's kind of the whole idea behind these polynomials. They give you really good approximations on a certain interval. You want a better interval, you gotta work out the calculus really to be sure you can get a better interval. But anyway, I hope you found this helpful, and maybe I'll be back in another video. Good luck.